Hello. Good morning, everybody. So, welcome to Signals and Systems. Let me get started. So, we'll start off with a brief recap of what we did last time. So, the last class we talked about a system that is linear and time invariant. So, again, the lecture is being recorded for your notice. So, this is linear and time invariant. So, any input of function xt will produce a corresponding output of yt. So what we said was, if we scale the inputs by some alpha, the output is also going to be scaled by the same alpha, right? Similarly scaled. If we shift the input or delay the input by tau, the output is also going to be delayed by tau. Similarly scaled, similarly delayed. That's all there is to it. So if you have a combination of different waveforms which are scaled by different amounts, the corresponding components of the output is also going to be scaled by the same amounts and delayed by the same amount. So we can write this mathematically, right? We can say, okay, we have the first amount scaled by alpha 1, x1, and we add to it a second component, alpha 2, x2, which produces x1 will normally produce y1, but because we scaled it by alpha 1, we will get alpha 1 y1. X2 will normally produce y2, but because we scaled x2 by alpha 2, what we get at the output side is alpha 2 times 1. Now, if we make it more complicated and also include the delays, we can write a more comprehensive version, which includes scaling and delays both. So we have alpha 1, x1, t minus tau 1, plus alpha 2, x2, t minus tau 2. We produce the outputs alpha 1, y1, t minus tau 1, plus alpha 2, y2, tau. So we are not restricted to 2 inputs. We can have any number of inputs, n inputs. So I can generalize the equation for the input x of t is actually defined as a whole bunch of different components. Let's say I goes from 0 to, or say 1 to m, or 1 to n. The scaling coefficients are alpha I, signal components are xi, t minus delay components are tau I. On the output side, we have y of t is actually defined as a whole bunch of components starting from 1 to n, alpha 1, yi, sorry, alpha I, yi, t minus tau I. Can you see the symmetry? Each component scaled by its own little alpha gain, own little delay tau, add them all together, it produces a waveform, and the output side follows the similar pattern. Right? The same thing that happens at the input just carries over to the output. That's all. Very simple, very, very simple. And that's all there is to it. Okay. So entire field of signals and systems for linear systems is that. We use this simple thing, and if you understand this very well, you can basically ace the course. This is what the course is about. But this simple phenomena of equal scaling at the input and output side, equal delay at the input and output side for all the different components of the signal is super crucial. That you really have to get what that means. Okay. So let's do an example. Let's take a picture so that we can drop it on the chat. Are you guys taking notes? All right. Let's say the above LTI system behaves as x of t is equal to n sine 2 by 100t produces y of t is equal to 20 sine 2 by 100t minus if x of t is, say, x1 of t is 11 sine 2 by 100t minus pi by 7 pi y bar. So notice here that the frequency is 100, right? So this is the frequency, and because it's a linear system, the frequency content doesn't change. It's the same shape. The only things that change are the amplitude given by alpha and the phase or the delay given by this value, right? So we change the input delay, we change the amplitude, but the frequencies remain the same in this example. The output frequency is remaining the same, no change, because it's a linear system. So I'll make a note of that. This is the frequency, 100 hertz, and it appears here too, 100 hertz. No change. This is the amplitude. And this is the amplitude scale. And this is the gain of x. So that's an important nugget. So if I can call this angle, let's say theta, theta is equal to omega times tau. So this is the 2 pi times f. This is the, so frequency times delay is equal to phase. So this is the phase. So to find the output for the new input x1 of t is very easy. You just plug into the formula. So we know that when the input is simply 10 times sine 2 pi 100t, the thing produces twice the size. So gain is 2, right? And 2 pi 100 minus pi by 3 time delay. So what is y? So I can write y of t by inspection. There's nothing to do. There's no math to do. We know that the gain, right? The gain is equal to 2. So we can simply write y1 of t is equal to the gain times the input, which is now 11. So it is 22. Frequency remains the same, sine 2 pi 100 t, right? And without any delay, it produces minus pi by. But here we have an additional phase lag, which is minus pi by 7.
Is there a formula for the gain? I know how you got the 2, but is there like a formula?
So gain is simply how much the output is scaled at the compared to the input, right? So the amplitude here is
Yeah,
is 10 and this is 20. So
it's just, okay.
again, just to remind you, the video is recorded. So whatever you say in class will be recorded. No, when you look at the output and you can see immediately gain has to be 2, right? So input was 10,
Oh, okay.
right? Yeah. Yeah. By looking at the input and output, you can figure that out. Okay. Now let's take a moment to look at some standard waveforms. So we know what a sine and cosine wave looks like, but is that the only waveform that we can experience? No, there is an infinity of possible waveforms. But in signal processing and signals and systems circuit theory, there are a couple of waveforms which we encounter all the time and are super important. So we give them special names and we kind of draw them and kind of figure them out so that we know what they are. So the most important waveform, or one of the most important waveforms, is a rectangular pulse. So let's say this is my input. Okay, this is my time axis. Unit is seconds, typically. Let's say this is x, this is let's say voltage. So I'll first start with a symmetrical rectangular pulse, which is defined as 0. Then you jump to a value, you come back, remains 0. So the region where it's non-zero, it's called the region of support. Or ROS. So by convention, we can call it what we want, but by convention, we normally say this duration is, let's say, tau. So this would be minus tau by 2. This point will be plus tau by 2. So it's nicely located symmetrically across the t equals 0 axis. Half of it is in the negative side, remaining half of it is in the positive side. And we take the height, this height, as standard A. So we can give this x sub r. R is for rectangular pulse. Rectangular pulse, right, is defined is equal to A for t from minus tau by two. Plus tau by two. 0 otherwise. So this is my region of support. So the region of support of a function is defined as the part of the domain. So this t-axis is the domain, the part of the domain where the function is not defined to be 0. So here we define the function to be 0. So that is outside the region of support. Inside the region of support, it is not defined to be 0. So it can be any value, which is a variable called a. So a can take any height. So this is the standard rectangular pulse. Now this pulse is very useful in signal processing, but it has a practical issue. See, half of it is in negative time. In reality, we really can't deal with negative time because it's in the before time equals 0, before the Big Bang, right? So we gotta bring everything into positive time. So this is called the causality problem. You have to make everything causal. So when we're actually doing something, we have to deal with waveforms which are only in the positive part of the time axis, and there's essentially nothing in the negative part. That's a practical caveat. But when you do that, the mathematics become a little complicated. So from a mathematical standpoint, we can use symmetry and say we can take into account negative time too. That's fine. But just keep in mind, when we actually do something, we have to add a bunch of time to make a big constant in time to shift everything to the positive side. Okay, but don't worry about that right now. So to keep things simple, we'll deal with the symmetrical waveform because it makes the math a little bit cleaner and easier to deal with as beginners. Okay. All right. So this is a rectangular pulse. So let's see how this rectangular pulse behaves when we insert it through a system which has some delays and other gains. Okay. So take a note of this, and then I'll erase, and then we'll move on. All right. So let's see when we have a simple linear and time invariant system, which I'm going to define like this. I'm going to have a gain is an amplifier, right? So here the gain is going to be G1 is equal to 3. Okay. And then I'm going to have component which is a delay 10 amperes. Okay. And then I'm going to add the outputs to produce my y. So this is called a signal flow graph. We'll give it a special name. We call it a signal flow graph. Or this Fg of the particular LTI. So the system I'm going to draw as a box. This is my LTI system. So it's got two components. This is a delay line, and this is an amplifier. So there are two branches. So these two things, right? We can show the direction of the signal flow using small arrows like this. This is where the signal is flowing, gets added and comes out. So it's a directed flow graph. There's a direction along each edge of the graph, right? So there are nodes which show whether the signal is splitting into two or multiple branches. So this is like a splitting action, right? And then you combine them using address or subtracts. So the signal flow graph allows you to express the same equations we wrote in the previous slide, the scaling, the delays, and the summation. The three operations that make up the linear time invariant system is represented here. This is the scaling, this is the delay, this is the summation, right? So this graph has the same information as the equation. The information and the graph are the same thing in different ways. So you need to have the skills to look at the equation and come up with the graph, or look at the graph and come up with the equation, because these are essentially telling the same thing. There is no information that is extra in one that is not available in the other. They are both the same, right? It's just two ways of representing. But this is kind of more visual, right? You can kind of see how the signals flow. Whereas if you are more abstract and mathematical, the math equation makes more sense to you. But they both mean exactly the same. All right, so let's see what this thing will do when you insert a particular pulse. I'm going to insert an XR of t with the following parameters. My amplitude is going to be 2. My delay tau is going to be, so not delay, my duration tau is going to be 3. So a pulse having amplitude 2, right? So what XR of t with these two parameters mean is that we have something like so. Tau is 3. So tau is equal to 3 and amplitude is equal to 2. Okay. We'll draw it a little bit bigger so that you can see. So the amplitude here is 2 and tau is 3. I'm going to put that input here, and that pulse is going to go directly, hit this amplifier and produce an amplified version that's get added here, right? And it's going to go through a delay and get added there. So the net result is going to be the resultant of two components coming from the two branches of the signal flow graph. The top branch will produce a scaled version without delay. The second branch will produce a delayed version without scaling. And the combination of these two at the summation node leads to the final resultant output waveform. So once you understand that, right, you can draw what the waveform is by inspection. You go from branch to branch to branch and see what the individual contributions are going to be from each branch. And the final output Y is the linear combination of the individual contributions from individual branches, right? So if you know how to figure out what each branch is doing, you add them all up, and that's the final output. So let's do it. It's pretty easy. So we have two branches. I'm going to call this one branch 1 and this one branch 2, right? So these are the branches. So my output, Y of t, is equal to something from the branch 1 plus something else from branch 2. So this is the output from branch 1. Output contribution from branch 1. This is the output contribution from branch 2. Got it? So easy peasy. Output contribution of branch 1 is simply a gain of 3, no delay, right? So we know what the pulse shape is for this. It's XR of t. So we have 2 times XR of t, right? The second one, there is no scaling, right, or unit scaling, scale by 1, but it's delayed by 10. So we can write the delayed version as simply no scaling. So 1 times XR of t minus 10. So we know what the output is in terms of the input XR, where XR itself is a rectangular pulse. But we know the shape of XR from here. So now we can plug in to every place where we have XR what this pulse is looking like, right? And we'll get the output. So I can now write it, or I can draw it. The first component is 2 times XR of t, no delay, right? So XR of t is something that is 3 wide and 2 tall. So 2 times that will mean the pulse is now 4 tall, but no delay. So we will get a non-delayed version that is 4 units tall. It's 3 units wide and now 4 units tall. So this is the contribution from branch 1. Or I'm just going to draw an arrow. So it is this. Okay. Then it goes to 0 and that's it, right? That's the first contribution. The second contribution is the pulse with unmodified height, but simply shifted by 10. So that one we can draw in a different color. So this part is simply delayed version of that. So we are going to get 0, 0, 0, 0, 0, 0, 0, and then we jump to 2. Okay. So now what is the total delay from here to here? We delayed it by 10. This duration is still 3. This height is still 2. So the final output is the combination of the red part of the waveform and the green part of the waveform, right? So let me draw it in black in a different graph, or let me draw it in blue in a different graph. So final output so the key point is this is going to jump to 4. This is 0. This is 3 wide. This is 2 tall. Sorry, 4 tall. So it goes like this, jumps up, jumps down, goes like this, jumps up, jumps down, continues. 2 pulses, tick, tick. The first pulse is height 4, second pulse, 10 seconds later, height 2. Okay. So your linear time invariant system started with, when you give it one impulse, one rectangular pulse, it produces 2 pulses, tick, tick out, right? The first one immediately comes out, but it's bigger. The second one comes out 10 seconds later, but the height is still the original, right? So you can create a linear time invariant system that produces a bunch of pulses at various times, at various heights, and you can scale the pulses by different amounts by depending on how much gain you put in each of the branches, right? So it's a magic box that converts a pulse into a bunch of pulses. But each individual pulse is exactly the same shape, but it produces a bunch of them, right? So in this example, by choice, we chose this delayed tau to be bigger than half of tau by 2, half of tau, right? So because of that, the green waveform doesn't interact with the first one. It's completely outside. Now, had I chosen tau to be, let's say, something small so that this starts before this stops. Then you are going to get the addition of the two and it produces a weird output, right? And that's valid. So that's a little bit more convoluted. So I'm not going to cover that in the first problem. But once you kind of figure this one out, let's do a case where the delay is a little bit smaller so that this starts before this ends. And you can see how it goes. Yes.
What does the one have the ability to possible contribution for branch two?
No, no, that's the point. So the branches 1 and 2 are completely independent, but they are just added up at this place. So the final output is a combination of all the components from the branches.
Where does the two come from? And two XRT? And all contribution for branch one and two, where did the two come from?
Oh, okay. So this is 2. So I made a, it is 2. It is 2. Good catch.
And thou, and the delay is not the same, is 10 and.
Right. So tau is not a delay. Tau is the duration of the pulse, right? And delay is 10. So it's delayed by 10, but its still duration is still 3. So delay is 3, right?
What does that mean? It's not like the time.
So it's a pulse, right? So it becomes 0. It jumps to, let's say, 2, and then it remains for 3 seconds and comes down. So it's a duration. So this is not a delay, it's a duration. It's a pulse duration. So let's call this the pulse duration. Yeah.
But the last lesson, the thou symbol was for delay, so it's in.
When tau is just a Greek letter, we can call it, you can call me tau, and then I'll be tau from that, Yeah. So you can call anything, but generally we can call it tau, we can call it t, we can call it mu, whatever you want. That's fine. Yes.
Alright, so basically on the graph, what the game does is that it changes the height of the graph.
Not basically, that's what it does.
Uh-huh.
Yeah, that's what it does. It changes the height of the graph. It
Uh,
scales it.
So.
No, it's not done yet. Yes. Yeah.
and also another thing,
Yes.
so how will you get tau from looking at the graph normally?
So by tau, do you mean the delay or the duration of the pulse?
Like the direction of the box, not the delay. The delay on
Yeah,
the-
I know it. So you cannot infer that from the graph, because that's a property of the signal that you apply to the graph, right? So I specified here that I'm giving XR of t. But I can take this same system and give it a sine wave, and it will produce a sine wave there.
Okay.
Right? So what you give as the input is not a function of what's contained in the system. Right? So next week we will actually build a system like this here, and we'll demonstrate how it works on the scope. You guys, what we are doing. Next Thursday. Clear? Yeah. Yes, Daniel.
So the red graph is the amplified is branch one, and the green graph is 2.
Yes.
Output.
Right? So had I put an amplifier here and put a gain here, this part will be scaled by that gain value.
So where does the number 2 on the grid graph comes from?
I defined it as 2, height 2.
Yeah, but in the output contribution branch 2, it says 1.
No, it says 2. This is 2.
In the expression is times
In the
one.
expression.
Oh no, so XR is scaled by 1. So when you multiply something by 1, it's just 1, right? So I could have just forgotten about it and just put XR of t, but I wanted to show that the gain is 1.
Oh, yeah.
Right.
Will the gain and tau always be given in these graphs?
Well, I mean, there's no such generality, like sometimes you might be asked to find out what the gain and the tau values are. It depends on the problem. So in this particular case, I defined these things as given. But as we get more and more into it, some cases you may have to find out what those values are based on something else. But you will always get enough information to figure out any missing stuff. All right, so let's do an example of the same system, but with different values of delay. So I'm going to keep this the same, okay? So none of this changes. The only thing I'm going to do is going to change my delay from 10 to a different value. So it's 3. So I'm going to change it to actually, let's say, I'm going to change it to 1. So now, the only thing that happened is I'm sending the same input without delay, gain of 2. So the first part of the output will not change. But the second one is going to change because your delay has changed, right? So what I want you to do is first work out what the two individual contributions from the two graphs, two branches are. Draw them on the same piece of paper, but maybe one with dotted, one with one solid, one dashed or something, or two different colors. And then you'll see how they cut in the time axis. So in the places where they are overlapping, you will have to linearly add the outputs to find the final output. Fine. Let's do it. You try it first.
If we could cut the equation. You know, the graph is graphing.
You don't have to, but why don't you do it?
Yeah.
Yeah. So let's do it. I'm going to do it along with you. So first start by the time axis, right? E. So the first part, branch 1, is the same as the previous problem. We have it jumping to 4
Duration is
and duration. So this is minus 3 by 2. This is plus 3 by 2. Duration is 3. Height is 4.
Same, but add.
So when you delay by 1 second, remember it is starting at minus 3 by 2. So you are going to be at half, minus half, right? Minus 1.5 plus 1 is equal to minus half.
It's just a random question, but -3/2, is that just something? How did you get, why did you?
Well, it's 3 wide and this is half of it is minus, is on this side. So 3 by 2 is half. 3 by 2. How do you divide 3 by 2? 1.5.
Oh, sorry.
All right. So this is negative 1.5, right? And you have to add 1 second from that. So the starting point is negative 0.5, negative half. So this is kind of like here. And the duration is just shifted by 1. Okay. And the height is still the same, right? It hasn't changed. So your height is going to be, I'll draw in green. Right? So the output is the sum of the red part, which is coming from the top branch, and the green part, which is coming from the bottom branch. So I'm going to draw the output. So it's going to come like so, jump to this point, remain like this, then it's going to go 2 up. And then come down. Is that right?
Wait, why is, so. Red part is 4, why did it go up by enough?
So this is the output. This is the y of t. Right? So the final output is the combination of the red part and the green part. They are getting added together linearly. So because we chose the delay to be smaller than the duration of the pulse, there is a period of time where both outputs of the branches are there at the same time. So the output is going to be the sum of both components, right? So there are places in the time axis where there's nothing, right? There are places in the time axis where one of the branches are producing the output, and then there's a middle part where both branches are adding to the output at the same time, so you get the net result. Yes.
Okay, so if I remember correctly, since the second part of YT overlaps with the first part, that means you gotta add the heights of both of those graphs, right?
Yeah, so it's a interference pattern. So it doesn't even have to be, when you add them, depending on the sign, it can actually be less. Right? So if I put in, okay, my gain for this branch is actually -1, whoop, it's going to come down. Right? So it doesn't always mean it's going to be bigger. Sometimes you might get 2 waveforms which are added. Each individual one is a big one, but when you add them together, they cancel out and get nothing out. That's possible. Right? So don't fall for that. I think this is correct, right? So we have this coming down. It remains at the green level and goes down. You got to do a problem, man.
What do you get?
Huh?
3/2.
3/2 is half the duration. 3 divided by 2. Duration is 3. Right? So this, we said that this is going from negative tau by 2 to positive tau by 2. So tau is 3, so 3 by 2 to positive. So let's do one more problem. So I'm going to change my A and tau values. I'm going to say, okay, A is equal to 1, tau is equal to 2. So my input now looks like this. Okay. My delay, I'm going to select as 2. And my gain here is going to be -1.
Good, fine, fine,
Hmm?
fine.
Yeah. So my new delay is 2. So it is 2. This depends gain 1. So that's fine. This one, gain is -1. So I'm going to draw the 2 graphs in the two separate colors. It's time. Okay. The first one, no delay, but scale by -1. So the same output, but inverted in phase. So we get something that jumps to -1. So this is now -1. Let's keep on the time. Delay is 2. So the second waveform starts at 2 delay. That means at this point, and the height is unchanged. It's the same pulse. So I'll get so this is branch 2. This is branch one. Right, so the next sum is the linear summation of the two branches. So my output basically follows a pattern like this. So it produces an output that jumps to negative -1. All right, so we'll stop there the lecture for today.